In this video, we'll be focusing on pressure. What is it? How do we measure it? And why is it important? Well, firstly, what is pressure? Pressure, we're looking at a force per unit area. And typically, we describe high pressure as there's a higher force per unit area and low pressure as a lower force per unit area. We can think of it as if we had a tube, a metal tube or something like that, and we put a bike pump on the end of it. If we pumped it up a lot, well, that would be a higher pressure inside that vessel. If we unscrewed it and let all the air out, well, that would be lower pressure. It might even be pressure that's within our normal atmospheric pressure range. If we put a vacuum on there and sucked all the air out of there, well, that would be a much lower pressure than our normal atmospheric range. Now, because pressure is force per unit area, we have our formula, which is force over area. Force we typically measure in newtons, and unit area we measure in square meters. And that gives us our Pascal unit, PA, which is our SI unit for measuring pressure. Having said that, PSI, pounds per square inch, is a common measurement for measuring pressure in several places around the world and in several applications in particular, like the pressure for our bike tires or car tires, for example, are still often measured in PSI. Another measurement that we have for pressure is atmosphere. And so we'll talk about that in a moment. Another one we have is bar. So pressure is one of these areas where we have quite a few different units that we can use to measure and quantify. So looking at pascals and bar, we know that 1 bar is 1,000 kilopascals. Likewise, we know that 1 psi is approximately 7,000 kilopascals. And 1 atmosphere, which is the standard pressure around us when we're at sea level, is a bit over 100,000 pascals. Now let's talk about the different types of pressure measurements. Now, mostly we'll be talking about pressure for fluids, liquids and gases, that is. But we can actually measure pressure for solids as well, because remember, it's just a force per unit area. So solids, we're looking at that contact area that our solid has with whatever it's making contact with, and the force applied between that solid and what it's applying with. Here's an example with these pyramids here. The pyramid that is upside down has a very high pressure on that little region there where the whole force is pushing down on one small spot. Now, if you flip it over to the right way up, the way that pyramids normally are, we have a much lower pressure region where we've significantly expanded the region of contact there, and we've kept our force the same, the force pushing down. And so we've significantly reduced the pressure there for this solid object. Now, as we move to liquids and gases, we move to some sort of a pressure sensor, and there's plenty of different ones. Before we look into all of those different pressure sensors though, there's a number of different terms that we need to define and understand around pressure. Firstly, we have total vacuum. And total vacuum is where we have zero pressure. We evacuate all the pressure, and this is what we have in space, where we have no atmosphere whatsoever. And so in this case, we'd have 0 pascals or 0 psi, and we often say psi-A or pascals absolute to denote that we're using absolute pressure here. We then have barometric pressure or atmospheric pressure, and here we're denoting the pressure that is wrought because of the atmosphere as the Earth. Now that pressure varies based on our altitude, for example. The higher up we get, top of Mount Everest, we have less pressure. The lower down we get, we have more pressure because of the weight of all the gases pushing down. I've mentioned already that 1 atmosphere, the standard atmospheric pressure at sea level, is about 100,000 kilopascals. And so it's interesting to think about that as we sit in our offices or in our chairs or in our homes or on the beach or anywhere else, except when we're up very high, of course, we've got about 100,000 kilopascals of pressure pushing against our body. And as we go up, well, that pressure decreases because we have thinner layers of our atmosphere at higher altitude. That term barometric pressure that we're talking about is a close cousin to talking about a barometer, where we're measuring our pressure and trying to predict weather patterns based on the barometric pressure or changes in barometric pressure. Is it going to rain soon, or is there a change coming, for example? Okay, let's talk about some of those other terms now. We talked previously about total vacuum, Well, we also have a vacuum, which is somewhere between total vacuum and atmospheric pressure. So we might have a vessel that we suck some of the air out of, and we have it under a partial vacuum. So that's what we refer to when we talk about vacuum. We have total vacuum, we suck all of it out. So a vacuum is somewhere between 0 psi and 1 atmosphere, or about 100,000 kilopascals. Then we have our absolute pressure, and our absolute pressure we measure with reference to total vacuum. So we say, okay, what's our pressure compared to what a total vacuum would be? And you can see in this diagram above, our green lines there, which are our measurements of absolute pressure with reference to that total vacuum value at the base there. Then we have our gauge pressure. Our gauge pressure is measured with reference to our atmospheric pressure. So if we've got a pressure that's higher than atmospheric pressure, our gauge pressure will be a positive value. If our gauge pressure is in a partial vacuum, our gauge pressure will be a negative value. And you can see that in the diagram above with those yellow lines there, where it goes positive or negative based on the actual pressure region that we're working in. If we want to work out at any point our absolute pressure, we can add together our gauge pressure and our atmospheric pressure. And that will give us what our absolute pressure is. So we can go between the two if need be. And then we also have differential pressure. We might want to measure the pressure between two different things, and neither of those things may be atmospheric pressure. For example, we may have a piece of pipe where one part of it's constricted and one part of it's not, and we want to measure the pressure difference between them. Or we might have a pressurized vessel and another pressurized vessel inside that vessel, and we want to measure the pressure differences between those different regions, which might have little bearing to do with our atmospheric pressure. And so there we have a differential pressure between those two different regions. Now, we often might get fooled into thinking that only high pressure is dangerous. Well, aside from being floating around in deep space without a spacesuit or something. But low pressure can be dangerous as well. When you do the maths, you realize that 1 atmosphere is about 100,000 kilopascals. Now, if you think about a meter structure, something that's 1 meter by 1 meter, so a meter square. And if you evacuate from one side of that, all the atmosphere, you suck it all out and create a total vacuum. Well, then you've got 100,000 kilopascals pushing from the other side on that particular structure or whatever it is. You do the maths there, that's essentially 10 tons worth of force pushing down on there. This is why there's been occasions where people have evacuated silos or created a vacuum on silos and cause the silos to crumple like our picture above here, because they haven't realized the amount of force required to actually hold out the outer atmosphere, the atmosphere that's all around us. When you create a vacuum inside these things, particularly a total vacuum, you've got a huge differential pressure between the two of them. And that can be quite dangerous.